What's the farthest apart you could put two electron domains? 180 degrees. So when you have two electron domains, and I'll explain what I mean by electron domains in a sec, the angle between them is going to be 180 degrees. Part of the Vesper theory you guys learned back in chem. Valence shell electron pair repulsion. Electrons, whether it be lone pairs of electrons or bonding electrons, they want to be as far apart as possible. They hate each other. They repel each other. So what about three electron domains? What's the farthest apart you can put three things? 120. Well, it is indeed 120. If we lived in a flat world, a two-dimensional world, what would be the farthest apart you could put four things? 90. It'd be 90. So, just everything right angles, right? But we don't live in a two-dimensional flat world, right? We live in a three-dimensional world. And the angle of farthest apart for four things is not 90 degrees. What is it? 109.5. If we take and turn this axis here, we can stretch out just a little bit further to 109.5. What do we call that shape? Tetrahedral. Okay. If we look, if you've got two electron domains, then you need two hybrid orbitals. If you've got three electron domains, you need three hybrid orbitals. If you've got four electron domains, then you need four hybrid orbitals. What's a hybrid?
Mix of two.
Mix of two things. So like your hybrid cars, they run on gasoline and electricity. So, or like, what do you get when you mix a horse and a donkey? A mule, something new. So hybrid, just a mixture of two things. So to make hybrid orbitals, you're actually mixing multiple types of orbitals, typically in organic chemistry, S's and P's. If you've got two electron domains, you need two hybrids. To make two hybrids, you have to mix two atomic orbitals, an S and a P. And so we just call those hybrids sp hybridized. And magically, those two sp hybrid orbitals we create point 180 degrees apart. So for three electron domains, you need three hybrid orbitals. To get three hybrid orbitals, you have to mix three orbitals. What are the first three available orbitals? S, P, and P. But to call it SPP would sound pretty dumb, so we call it sp2. And then four electron domains, sp3, made from one s and three p orbitals for a total of four orbitals for four electron domains. Put a rather large molecule up here for just a sec. Represent it with what you guys have seen as condensed structure. It's not exactly a line angle structure. We could totally make a line angle structure out of it. We got a 1, 2, 3, 4, 5, 6, 7 carbon chain. So we can make a line angle structure out of it if we wanted to. Here I made the alkene trans. So our condensed structure doesn't show if it's cis or trans, I picked one. Could have just as well picked cis. All right, my question is, what is the hybridization of that carbon right there? sp3. The next carbon over. sp3, how do you know?
4 bonds.
Yeah, it's got 4 bonds in this case. It doesn't have to be 4 bonds, but 4 electron domains. Well, it's bonded to a carbon here, and 2 hydrogens. So every atom you're bonded to is an electron domain. Notice it's not every bond, but every atom you're bonded to, or any non-bonding pair of electrons is an electron domain. So what about this guy? sp2. He's only bonded to 3 atoms and has no lone pair. He's bonded to this carbon, the hydrogen, and this carbon. So again, whether it's a single, a double, or a triple bond, that's just one atom we're bonded to. So it just counts as one electron domain. So this guy here, sp2, this guy here, sp2. And these two, sp2. Cool. So you should very quickly be able to figure out the hybridization of any atom in any structure I give you. Cool. There are 2 types of bonds in organic molecules. What are the 2 types?
Sigma, pi.
Sigma and pi bonds. So one of these has a much more specific definition than the other. Which one?
Sigma.
Actually, it's pi. The pi is a much more specific definition. A pi bond is the sideways overlap of 2 p orbitals. They overlap both above and below the internuclear axis between the 2 atoms. But that's just one pi bond. So pi bond is a very specific definition. Notice pi is a letter in the Greek alphabet. It is analogous to what English letter? P. And a pi bond is made from the sideways overlap of p orbitals, period. Nothing else. Only p orbitals, only sideways overlap. So sigma bonds result from the end-to-end overlap of any kind of orbital you can think of. S's, P's, or any of the hybrids as well. They're not specific in terms of which orbital. And it's end-to-end overlap instead of side-to-side. So you could have 2 s orbitals overlapping. You could have an s orbital overlapping end-to-end with a p orbital. You could have 2 p orbitals. Overlapping in an end-to-end fashion. You could also have a hybrid orbital of some sort involved in making a sigma bond as well. These are all sigma bonds. So pi bonding, very specific, only p orbitals and only sideways. Sigma bonding, it's end-to-end overlap instead of sideways. And anything is capable of participating in sigma bonding. Here's the deal. All single bonds are sigma bonds, all of them. Every last one of them. Any single bond is always a sigma bond. And it turns out the first bond any 2 atoms makes is a sigma bond, but you can only make 1 sigma between 2 atoms. So if you've got a double or a triple bond, the first one's definitely sigma, but every additional bond is a pi bond. So my question here is, in this molecule, how many sigma bonds are, actually let's do easier question first. How many pi bonds are present?
The entire molecule?
The whole molecule.
3.
The 3 or is it 4?
4.
So a double bond is 1 sigma and 1 pi. So I got one pi there and 1 pi there, but a triple bond is 1 sigma and 2 pi's. So this thing does indeed have 4 pi bonds. How many sigma bonds? This is tougher to count. It's tougher to count because I didn't draw all the bonds to the H's, which a lot of students forget. A lot of students see something like this, like, oh, 1, 2, one of them there, that's 3, 4, 5, 6, 7. And that's definitely going to be one of the multiple choice answers, but it's not right. You got to all the single bonds of the hydrogens count as well. So we got 3 there, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. What is this carbon using to make its pi bond with this carbon? P orbital. What's this carbon using to make that same pi bond? P orbital. If I say pi bond, you got to say p orbital. Works that way every time. But if I say, what's this carbon using to make the sigma bond with this carbon? Well, sigma bonds can be used making, can be made using anything. If an atom is unhybridized, it'll use its unhybridized orbital. Like hydrogen uses an s orbital. But if an atom is hybridized, it will always use a hybrid orbital to make the sigma bond. Is this atom hybridized? Yeah, so what orbital is he going to use to make any of his 3 sigma bonds? An sp2. What's this carbon going to use to make that sigma bond? sp2 as well. So the sigma bond between these 2 carbons is made from the overlap of an sp2 from this carbon with an sp2 from this carbon. So what about these 2 carbons? What 2 orbitals are overlapping to make their sigma bond?
sp2 and sp3.
Yeah, an sp2 and an sp3. Just look at their hybridization designations. So if we're talking sigma bonds, they're going to use a hybrid if they are. So what about this carbon to one of its hydrogens? What orbitals are overlapping to make one of those sigma bonds? sp3 and one of the hydrogen's s's. Good. An sp3 and an s. Sweet. So let me ask you guys another question. What if I were to actually have drawn those h's out? So in my drawing, being somewhat of a Lewis structure here, what does this angle look like it is? 90. What is it really? 109.5. So let me ask you a different question. What is the angle from this hydrogen all the way to this carbon? What is the CCH angle? 109.5. Looks 180, but again, doesn't matter what the angles look here. This thing is sp3 hybridized. All of the angles around it are all 109.5. Whether they look like they're 90, whether they look like they're 180, they're all 109.5. What's the hybridization of the nitrogen? sp3. Yeah, he's got 3 atoms he's bonded to, plus a non-bonding pair of electrons for a total of 4 domains. So he's sp3 hybridized. So what kind of orbitals are overlapping to make one of the sigma bonds between nitrogen and hydrogen? sp3 and s. What kind of orbital is the lone pair in? An sp3. So the nitrogen's sp3 hybridized, he puts the lone pair in an sp3 hybrid orbital. So what are the angles? What's the hydrogen-nitrogen-hydrogen bond angle?
170.
Yeah, turns out it's just a little bit less than 109.5. So the electrons in this sp3 hybrid orbital here have a little more repulsion. So to the bonds and all the hydrogens, and so they get scrunched down just a tiny bit, just a little bit less than 109.5. You by all means don't have to know that the angle is 107, you just got to recognize that it's a little less than 109.5. So one other thing. Anybody remember what this molecule is? That's formaldehyde. What do we use formaldehyde for? Yes. Preserving dead bodies. So, nothing about formaldehyde here, but I want to know what the influence of a double or triple bond is on bond angle. You won't have to worry about it with a triple bond because it's going to be linear regardless. But with a double bond, there's 4 electrons here instead of the normal just like 2 here. And as a result, it's got a little bit more of a repulsion on these 2 other bonds as well. And because it's got a little more repulsion, what's this angle down here going to be? Well, it's going to be a little less than 120. So, and what are these angles up here going to be? A little greater than 120. So pi bonds can affect the angle as well. You'll more commonly see them asking you questions involving a lone pair affecting the bond angle, but pi bonds can do the same thing, or at least a similar thing. Questions?